Ladies and gentlemen, welcome to lecture number 11 in Calculus 1 with the applications. Well, this will be a very important lecture because we will be talking about techniques of differentiation. So in other words, you will find out how to compute derivatives, what kind of rules you should use, and so on. I decided to include also some other part from this chapter just in one lecture. So basically what I'm going to do in this lecture will be the following. I will cover not just the usual techniques of differentiation, but also I will be talking about derivatives of logarithmic and trigonometric functions, exponentials and so on. And also at the end, I would like to talk also about the chain rule, because you will see that the chain rule will be just a generalization of, well, it depends. You apply it for different rules that we will learn in the techniques of differentiation. All right, so let's get started. So I'm going to start with something easy first. So we will learn how to find the derivatives of some easy functions. So some easy rules first. So let's start with the, as you can see in the title, it is techniques of differentiation and chain rule. So we will, I would like to do that separately, but well, in the same lecture. Well, let's start with techniques of differentiation. All right, so we'll start with this first. And well, the first thing that we have, so it's, let's say, a theorem 1, let's call it like a theorem, will be the constant rule. And let me write this with a different color. Well, in fact, basically this says that a constant function, let's just say f of x equals k, right? Has derivative, or let's say has a derivative, or maybe it has the derivative, f prime of x equals 0. So the derivative of the constant function will be 0. Keep that in mind. For example, if the derivative of 2 will be 0. So the derivative of 1 million, again, it will be 0, right? So keep this in mind. All right, and let's write this. We will write it in this way. The derivative with respect to x of this function, f of x, which is the constant k, will be 0. So this is what you need to know. All right. So this is the first rule, the constant rule, let's call it. Now, another, as you can see, this is quite easy to see. The second one, theorem 2, let's just say this will be the power rule, right? And it says the following: for any, let's say, a real number n, right? The power function and this power function is f of x equals x to the power n, has a derivative f prime of x, so we'll denote it in this way, will be n times x to the power n minus 1. In other words, we can write this in the following way. The derivative of d with respect to x of x to the power n of this function, it will be nothing else than just n times x to the power n minus 1. All right. So this is the power rule. And now let's give a simple example so that you see exactly how this works. For example, if we take f of x equals x to the power 8th, quite clearly the derivative of, let's say, df over dx will be nothing else, right? The derivative of that with respect to the variable x. So this is how you read this, right? This will be nothing else than just 8 times x to the power 8 minus 1, which is 7, right? As you can see. All right, now what we're going to do is I'm going to give you some rules, some procedure of how to, when you have two functions and you would like to find the derivative of the sum, of the difference, of the product, of the quotient, and so on. So let's call this theorem 3. And we'll call this, let's say, basic rules for combining derivatives. So we will see some procedure, some standard procedure of finding the derivatives. And I'm just going to draw a chart here. I'm going to do it in the following way. Okay, let me do it in this way. Okay, so we'll have 3. Here I'm going to put the name of the rule. Right? Let's keep that. The function notation. And also like to, since some of you will see this in the physics class, I would like to use the Leibniz notation as well. So that you can get used to both notations, not just f prime. Also, you can see the derivative of f with respect to x and so on. All right, so let's keep going. And the first thing is the constant multiple. In fact, let me write this with a different color. Constant multiple. And here, the rule is the following. So if I have a constant, let's say k times f of x, and everything prime will be nothing other than just k times f prime of x. So that's the function notation. And now if we want to write this in terms of Leibniz notation, so it will be the derivative with respect to x of k times f, which will be nothing else than just k times the derivative of f with respect to x. Okay. Now, the other thing that we need to worry about, so this is the constant multiple. As you can see, it's pretty easy. Now, let's see what happens when we have the sum rule. Well, as you can imagine, the derivative, if we add two functions, let's say f and g of x, and we want to find the derivative of this, this will be nothing else than just f prime of x plus g prime of x. In other words, the derivative of the sum is the sum of the derivative. And in Leibniz notation, we can have the derivative with respect to x of f plus g is the derivative of f with respect to x plus the derivative of g with respect to x. Now, well, similarly, we have the difference rule. Let's write it here as well. You can look in the chart. This is, as you can imagine, it's very similar to the sum rule. Well, the difference is actually a sum. You just add the first one with the opposite of the second function. So as you can see, the derivative of f minus g will be nothing else than the derivative of f minus the derivative of g. And of course, in Leibniz notation, it will be similar. df over dx minus dg over dx. Okay. So these are the basic rules, but now let's also let me say the linearity rule. I want you to see this one. Well, it's pretty straightforward, but let's just write it. For example, if I have a constant a times f of x plus a constant b times g of x, everything prime, right? This would be nothing other than just a times f prime of x plus b times g prime of x, right? And in Leibniz notation, if you want to write this, we can write this. In fact, you know what? Let me just, I don't want to, let me do it like this. So this would be a times f prime of x plus b times g prime of x. And in Leibniz notation, we can write this in the following way. So we can write this daf plus bg with respect to x will be nothing else than just a times df with respect to x plus b times dg with respect to x, right? Now, a very important rule, and let me write this with a different color because I want you to see that it's a bit different. It's not as you might, as you may expect. We call this the product rule. So the product rule, as you will see, it involves the derivative of the product of two functions. So let's say we have f times g, and we want to take the derivative of this guy. Unfortunately, this is not the same. It doesn't behave as the derivative for the sum. When it will look something like this. So it's f prime of x times g of x plus g prime of x times f of x. In Leibniz notation, you will have that d fg over, well, with respect to x will be nothing else than just g df with respect to x plus f times dg with respect to x. And now finally, another special rule that I would like to mention is the quotient rule. And pay attention here, this holds provided that the function on the bottom, on the denominator, is non-zero. In other words, this will involve the derivative of the quotient of two functions. So it's f over g, everything prime. This will be f prime of x times g minus g prime of x times f of x, everything over g squared of x. So this is how we're going to write this. Or if we want to write this in Leibniz notation, this would be, it can be written in this way. So this would be G df with respect to x minus f dg with respect to x, everything over g squared. All right, I want you to look at these rules. These are the rules. The most important rules, I would say. And of course, I would like to mention one thing, but as you can imagine, the linearity rule can be generalized to n functions, right? It doesn't hold just for 2. You can do this for 3, for 4, and so on. Okay, so these are the rules, and we're going to operate with them in what will follow, and we'll do plenty of examples. And let's just start doing this. So let's see exercise 1. Which says the following. Find the derivatives the first derivative, the derivative of the following functions. I just say the first one will be f of x will be, let's say, 2x squared minus 5 square root of x, right? B, f of x will be, let's say, 3x squared minus 1 times 7 plus 2x cubed, right? Let's see what other examples. C, let's take the quotient, a rational function. F of x will be 4x minus 7 over 3 minus x squared. And D, let's say f of x will be equal to, although this is the composition of a function, but anyway, let's get 4x plus 3 everything squared. All right, so these are the two functions. These are the 4 functions that we, and we want to find the derivative of these functions. Well, as you can see, if you look at them, if you look at these functions, the first one is just a combination. As you can see, there are 2 functions. There is the quadratic function and the square root of x, but it's a linear combination between these 2, whatever. B, you see the function from B is the product of 2 functions of quadratic and cubic function. The function from C is the ratio of 2 functions, of a linear function and a quadratic function. And the last one is just a function squared, a linear function, the square of a linear function. All right, let's do these problems. Let's see the first one. Well, if we want to look at the first one, well, I will write this in Leibniz notation if you want. So we have, this is just computational, the derivative with respect to x of f of x. Let's write it in this way so that you can see what is the function here. Is nothing else than just the derivative with respect to x, and now we will replace f by 2x squared minus 5 root square root of x, right? And now we're just gonna apply the basic properties of the derivative as we have seen above. So this would be nothing else than just the derivative with respect to x of 2x squared minus the derivative with respect to x of 5 times square root of x. Now you see we can apply the constant rule. So we apply the difference rule now. Now we can apply the constant rule. So we can take these constants. If you look at them, these guys here, this 2 and 5, we'll take them out. So this would be equal to the derivative with respect to x of x squared minus 5, the derivative with respect to x of square root of x. Well, we can apply the constant rule now. So this would be, in fact, let's rewrite this a bit. So it will be 2 times the derivative with respect to x of x squared minus 5 times the derivative with respect to x. And this square root, we can write this as a power function. So this will be x to the power 1/2. And this would be equal to, if we look at this will be 2 times the derivative with respect to x of x squared is 2x, is 2 times 2x, let's write it in this way, minus 5. And the derivative of x to the power 1/2 will be nothing else than just 1/2 x to the power 1/2 minus 1. So 1 minus 1/2, right? And if we do the algebra here, and if you, this is 1, so this would be 4x minus 5 over 2 square root of x. So this is the derivative. This is how we compute the derivative of the first function. So we can write in the following way. F prime of x, if you want to write it in, is 4x minus 5 over 2 square root of x. Okay, B. Now let's look at the second function. As you can see in the second function is the product of two functions. So we will definitely apply the product rule. So by the product rule, we have the following. The derivative with respect to x of f of x. But keep in mind that this f of x is the product of two functions. So this would be the derivative with respect to x of. And now let's write the functions. The first one is 3x squared minus 1. And the second one is 7 plus x cubed. And now we actually apply the product rule. And this would be nothing else than just, if you want, 3x squared plus 1 times the derivative with respect to x of 7 plus x cubed plus 7 plus x cubed times the derivative with respect to x of 3x squared plus 1. So this is actually, we apply the product rule. So this is where we apply the product rule here, or this equality here, right? And now once we look at this, we know how to compute the derivative of each. So this would be 3x squared plus 1 times the derivative of this guy here. If you look at this guy here, the derivative of this will be nothing else than just what? So that will be the derivative of 7. So we apply the sum rule. But anyway, I'm just going to skip it. So it will be 0 plus the derivative of x cubed, which will be 3x squared. So it will be, we'll put here 0 plus 3x squared. Right? Wait. Did I forget anything? It's a 2 here. I'm sorry. Forgot to put here a 2. Here a 2. Yes. And now it will be a 6 here. 6x squared. Okay. Plus, and now let's look at the second one. So the second one will be 7 plus x cubed times the derivative of this guy here. So this guy here, so this is 0 plus 6x squared. And this guy will be what? Will be 6x plus 0. So this will be 6x plus 0. And anyway, and now this is just a bunch of trivial algebra. And at the end of the day, once you do the algebra, I'm just going to skip it directly. So I'll leave this to you as a computation to figure it out. This will be nothing else than just 6x times 5x cubed minus x plus 7. This is what's it. So we can write f prime of x is 6x times 5x cubed minus x plus 7. So this is how we're going to find the derivative of this guy, right? So this is the derivative. All right. Now let's see the third one. Let's see, what do we have in the third one? We have the quotient of two functions. Whoa. Here we apply by the quotient rule. Right? What do we have? We have that that the derivative of f with respect to x, so this would be nothing else than just the derivative with respect to x of, and I'm just going to write this here, so it will be 4x minus 7 over 3 minus x squared. And this would be equal to, now we actually apply the quotient rule here. At this moment we apply this, and this will be equal to the following. So I'm going to write it in this. So I'm going to write it in this way. We're going to have a fraction here. I'm going to put here on the bottom will be 3 minus x squared, everything squared. That will be my function. So the function on the top is f, the function on the bottom is g. And now this would be the derivative with respect to x of 4x minus 7 times 3 minus x squared minus 4x minus 7 times the derivative with respect to x of 3 minus x squared. All right, so, and this will be equal to, once we do all this, so this will be 3 minus x squared times 4, right? Minus 4x minus 7 times negative 2x, everything over 3 minus x squared, everything squared. Now we're going to do this algebra, and again, I'm just going to skip it anyways. You can figure it out directly what this is equal to. So this will give us, if we look at it, you can do actually the computations quite easily. So this will be 4x squared minus 14x plus 12, everything over 3 minus x squared, everything squared. So that's the derivative. So we can write f prime of x as 4x squared minus 14x plus 12, everything over 3 minus x squared, everything squared. All right, so this is, and now the last one, well, you know how they say we save the best for last. The last one can be also, it can be done using the chain rule, but I don't want to spoil it for the moment. So I'm just going to do it, I'm just going to expand the function. So we have that, the derivative, and we're going to write it in this way. With respect to x of 4x plus 3, everything squared, right? This would be nothing else than just the derivative, and now we're going to expand this. So this would be 16x squared plus 24x plus 9. And now this will be nothing else than just the 16x squared plus the derivative of 24x plus the derivative of 9. And now, computing each one of them, well, we're just going to apply what we said, the extended linearity rule, right? We said for linearity we have 2 functions, but now we have 3, and we said that we can have n functions, whatever. So the first one will give you 32x plus 24, and the last one will be 0, and that's your function, right? So we can write that f prime of x is nothing else than just 32x plus 24. And that's the end of the problem. So we computed for the derivative, the first derivative of 4 functions. And now let me, well, as you can see, I think this is pretty relevant example. Now you can figure it out how to compute derivatives of other functions of this type. But now we said that we only talked about compute the derivative. So when you are asked to compute the derivative, you always think of the first derivative. But there is a question. Is there a second derivative, a third derivative? And the answer is yes. And now let's talk about this, higher order derivatives. All right. The philosophy is the following, because the derivative of a function is also a function. The differentiation can be applied over and over. Can be applied over and over, right? As long as the derivative itself right is a differentiable function, In other words, we can apply the derivative as much as we can until there is nothing we can do. Let me draw the following chart. In fact, so here we will say derivative. And here we'll talk about notations. And now let's look first derivative. Right? We will have y prime, or we can also have the following. We can write this as f prime of x, or sometimes we just write in Leibniz notation dy over dx, right? We have the function y, so function of x, and we take the derivative of the function y with respect to x. Now the second derivative we will denote it in this way. So we will write this as y prime prime, which is y second prime, or you can write this f second prime of x, or you can write we compute the derivative twice of the function y with respect to x. So we write this d squared of y over dx squared. So this is how we're going to write it. Well, keep in mind that here we have y prime prime. Now the third derivative, let's write one more. Is y prime prime, so we have three of them. Or sometimes if you don't like it, you can just put it like this. Or you can write this 3 in parentheses, or in Leibniz notation will be d cubed y over dx cubed. All right, and we keep going. And the nth derivative will look like this. I'm going to write it in this way, n, right, the nth derivative, or like this. Or if you want in Leibniz notation, d to the nth of y over dx to the n. So just like I said, the second derivative is the derivative of the first derivative, right? And please keep in mind that this f to the power n, so remark, let me point out this important remark, because I don't want you to mess the two. The nth derivative of a function is not the same as the nth power of a function. Keep that in mind. So this is the nth derivative, and this guy is the nth power of f. They're not the same. Keep that in mind. All right, so this is a story with higher order derivatives. And now I would like to do a problem. You see, now we computed some derivatives, the derivatives of some functions using the rules that I just mentioned at the beginning of the lecture. But now I would like to do another problem, so exercise 2, where I will have to use the definition. To find the derivative. All right, and the problem states the following. So use the definition to find the first derivative of the so this is important, of the following functions. Okay, the first function is f of x, and I'm just going to take now a combination of quadratic linear functions, and linear functions. So it's 2x squared minus 16x plus 35. And the second one will be g of x is, let's say, x over x plus 1. Of course, you can use the rules that we have learned, but let's use definition as well. And let me remind you that the derivative of a function at a point is nothing else than the limit of the difference quotient. So recall that let's write in words that the derivative of the function f at the point x naught is given by the following formula. So it's f prime of f at x naught, which is nothing else than the limit, if you want to write it in like this, as x approaches x naught of f of x minus f of x naught over x minus x naught. Or equivalently, let's write the definition with delta x. We can write this above definition as the limit. So we say that f prime of x, let's say, is the lim as delta x, as this difference approaches 0 of x of f of x plus delta x minus f of x, everything over delta x. So both of them are equivalent. But now you can use either one. In previous lectures, we used the second one, right? But it doesn't really matter. You can use the first one as well. And now let's see. So we have, so using this definition, we have the following, that the derivative with respect to x of f is nothing else than just the lim as delta x approaches 0 of, now let's write the definition, x plus delta x minus f of x, everything over delta x. And this would be nothing else. Oh my, and now let's look at our function. Whew. So I'm going to write, okay, this would be equal to the lim as delta x approaches 0. Let me write it like this. As delta x approaches 0 of the following. So on the bottom we have delta x, and on the top we have, so our function was 2x squared minus 16x plus 35. So this would be 2 times x plus delta x, everything squared, minus 16 times x plus delta x. Okay, plus 35, minus f of x. So minus 2x squared plus 16x minus 35. Okay, right? All right. And this would be equal to the limit as delta x approaches 0 of. And now we, by doing all this, foiling everything and doing all these computations, so this would be equal to 2 times x squared plus 2x delta x, right? Plus delta x squared minus 16x minus 16 delta x plus 35 minus 2x squared plus 16x plus minus 35. As you can see, they will go away. So this would be, if we want to write this, this would be nothing else after some computations, that this is the lim as delta x approaches 0 of 2x squared will vanish with this. So this will be 4x delta x times delta x, right? Plus 2 times delta x squared minus 16 times delta x, everything over delta x. And now we can factor here. We can factor a delta x, and this would be nothing else than just the lim as delta x approaches 0 of the following. Let's put this delta x, so this would be delta x here times 4x plus 2 delta x minus 16. These two will go away, so this would be nothing else than just the lim as delta x approaches 0 of, in fact, there is no fraction anymore, of what? Of 4x plus 2 times delta x minus 16. And this would be nothing else than just, well, if you plug it in for delta x approaches 0, this would be nothing else than just 4x minus 16. And guess what? That is the derivative. So this is the derivative of the first function. So we can say that the derivative of f is 4x minus 16. Now let's see the second part, because we had two functions here, yeah? The second one. So for the second one, we have this function. So g of x is x over x plus 1. Of course, if you want to use to find the derivative, you can apply the quotient rule, and you can write it in very rapidly, I would say. It's very fast. But now we're asked to use a definition, and although it will be a bit painful, but we can do it. So let's use the definition. So we have that using the definition. We have the following. We have that the derivative of f with respect to x will be, by the definition, the limit as delta x approaches 0 of, and here on the, it will be f of, by the definition, this is f of x plus delta x minus f of x, everything over delta x, right? And now we're just going to put everything together. So this will be nothing else than just the lim as delta x approaches 0 of, and now let's be careful here. I'm going to write it in this way. So this would be x plus delta x over x plus delta x plus 1, right? Minus x over x plus 1. And I'm going to put here 1 over delta x times 1 over delta x, right? It's the same thing. So this would be the lim as delta x approaches 0 of, and now let's do the computation. So by doing some algebraic manipulations here, this would turn out to be equal to x plus delta x times x plus 1 minus x times x plus delta x plus 1, everything over x plus 1 times x plus delta x plus 1. Everything over 1 over delta x. All right, beautiful. Now let's keep going. This would be the lim as delta x approaches 0 of the following. We have to be careful with the computations here. I would like to go step by step because I don't want to do any mistakes. So we're going to have this fraction. And here at the end will be 1 over delta x. And now let's see. So this would be multiplying all this will give us x squared plus x plus x times delta x, right? Plus delta x minus x squared minus x times delta x minus x, right? And now on the bottom we have x, let's keep it like this, x plus 1 times x plus delta x plus 1. And this will be further equal to, well, everything will just cancel here. If you look, basically I'm just going to have so this would be equal to the lim as delta x approaches 0 of, now let me see if I yeah, so this would be the lim as delta, yeah, we'll have the last term will be a delta x, so this will be delta x over x plus 1 times x plus delta x plus 1 times 1 over delta x. These two will cancel, so this would be nothing else than just the lim as delta x approaches 0 of 1 over and x plus 1 times x plus delta x plus 1. Well, and now it becomes clear that as delta x approaches 0, this will be nothing else than just 1 over x plus 1, everything squared. So that's the final result. And this is the derivative of this. So we can say that g prime of x is 1 over x plus 1, everything squared. Okay. Of course, like I said at the beginning, you can use the quotient rule to find the derivative of this, so there will be no problem. Of course, now I can also ask what is the second derivative of this function, what is the third derivative, and so on. But I would like to skip this a bit. I'm sure you can do this, and probably I will do this kind of problems maybe at the review session before the midterm. I would like to stick more in computing derivatives and maybe using the computations of derivatives in different problems. All right, now I would like to veer towards another problem. So exercise 3. And in fact, I have in my notes, I did for the same functions to compute the second derivative and third derivative and so on. So you can do it. You don't have to use the definition. You can use the rules. But anyway, I'm just going to skip this for the moment. I want to stick to the essential. Now, the problem says the following. Let's consider the following function. So consider the following function. And I'm going to consider the following rational function, which is 3x squared plus 5, everything over 2x squared plus x minus 3. So the first thing that we're asked to do is to find the equation of the tangent line at x equals -1. The second part is to find the equation of the normal line at x equals -1. Okay, so this is the problem. Well, both of them will involve computing the derivative of this, right? So the equation of the tangent line, the equation of the normal line. So this will involve, in the first part, for the first part, this will involve the computing the derivative. So the derivative of f, right, is given by, and I'm just going to write it directly. I'm going to leave this to you as an exercise to do it. Is given by f prime of x. So this would be nothing else than 3x squared plus 5, everything over 2x squared plus x minus 3 prime. And by applying the quotient rule here, so I'm just going to write it. So here is the quotient rule. This would be 2x squared plus x minus 3, everything squared. And here, this would be, let's just write it, 3x squared plus 5 prime times 2x squared plus x minus 3 minus 2x squared plus x minus 3 prime times 3x squared plus 5. All right, so this is the quotient rule. And after some computations, so I'll leave this to you as an exercise here. You know how they say, so these details, I'm going to leave them to you. But I would appreciate, in fact, it's for you, it will be very good if you actually verify these details. You know how they say the devil is in the details. And this will give us, okay, I'm going to put here details. So this is an exercise for you. It will give us, well, I haven't written somewhere. Where is it? Okay, so this would be 3x squared minus 38x minus 5, everything over 2x squared plus x minus 3, everything squared. So this is the derivative. Anyway, the details are missing, but I think you can compute that. I'm sure you know how to compute the derivative of 3x squared plus 5. You know this is 6x, or the derivative of 2x squared plus x minus 3, which is nothing else than just 4x plus 1. Okay. Now let's evaluate the derivative. Now, f prime of x, let's evaluate it at x equals -1. So this would be 3 times -1 squared minus 38 times -1 minus 5, everything over 2 times -1 squared minus 1 minus 3, everything squared. And this will give us equal to 9. And this guy here is nothing else, so let's write it, the slope of the tangent line at the point x equals -1. That's what it is. So this is number 9 here. Okay. This implies that the equation of the tangent line is given by the following. Let's write it in this way. So y is f prime, the derivative of f at the -1, and we evaluated this, times x minus -1, which will be x plus 1, plus f of -1. And f of -1, let's write it here. Let's evaluate this. This will be 3 plus 5 over 2 minus 1 minus 3, which is -4. Okay. So this would be equivalent with y. So the derivative is 9. So it's 9 times x plus 1 plus -4, or y equals 9x plus 5. So that is the equation of the tangent line, right? Okay, so this is basically, you just need to find the derivative. But now, how to find the equation of the normal line? So what do we know about that? Let's see the second one, the second part. So first of all, the normal line, right, will be perpendicular. And we know that the product of the slopes, so the normal line will be perpendicular on the tangent line. So this will imply that the product of the slopes is -1. So the slope of the normal line is equal to -1/9. And now we know that the normal line passes through the points of coordinates -1 and f of -1, which will give us -1 and -4. So we have that y is, we write this equation of the normal line in slope intercept form. So this would be, this will give us that that y is -1/9 times x plus b. And now we need to determine b, and probably you know how to determine the b. So now we plug in this point of coordinates, let's say -1, -4, to determine b. So we will plug it in, and we will have that -4 is -1/9 times -1 plus b. And from here, after some computations, it will give us b, so 36, it will be -37/9. And therefore, the equation of the normal line is given by y equals -1/9x minus 37/9. And that's it. So this is how we find the equation of a normal line. So first of all, we depend on the equation of the tangent line. So we can do this. All right, now before veering towards, well, I have some other stuff, veering towards the derivatives of trigonometric functions, exponentials, and maybe chain rule. Let me do one more problem. And probably, okay, so this would be problem number exercise 4. Which says the following. Let's consider the following function. Consider the function And we're going to consider, we will take the following function. F of x will be x minus 2 times x squared plus 4x minus 7. And what we're interested here is to find all points right on this curve where the tangent line is horizontal. Okay. Well, we would like to see when the tangent line is horizontal. We like to address this. So when is this horizontal? Well, the tangent line is horizontal if the tangent line is horizontal, then the slope of the tangent line is 0. In other words, the derivative of f is 0. So that's what we know, right? In other words, now we can compute the derivative. So a computation of the first derivative of f gives us that f prime of x will be, well, you see you have the product of the two functions. So this would be, let me write it in this way. So it's x minus 2 times x squared plus 4x minus 7 and everything prime. So we apply here the product rule. And this would be equal to x minus 2 prime times x squared plus 4x minus 7 plus x squared plus 4x minus 7 prime times x minus 2. And after some computations, again, the devil is in the details, this will give us, so details, and I'll leave these details to you as an exercise. This will be equal to 3x minus 5 times, let me look at the notes, times x plus 3. So that's the derivative. And now we know that the tangent line is horizontal. So this implies that the derivative is 0. So since f prime of x is 0, right? We have that 3x minus 5 times x plus 3 equals 0. So this guy is 0. Okay, so this implies that x is either 5 over 3 or x is negative 3. Now at x equals 5 over 3 and x equals 3, the tangent line is horizontal. Is horizontal. Okay. So now let's compute f of 5 over 3. Let's evaluate this. This will give us something like 22 over 37, over 27, sorry, negative 20. And f of 3 is 50. And we can say that the point 5 of coordinates 5 over 3 and negative 22 over 27, and the points 3 and of coordinates 3 and 50, the tangent line is horizontal. So and that's the end of the problem. So basically, it's just the main ingredients is to note that the tangent line is horizontal. If the tangent line is horizontal, then the slope of the tangent line is 0. So therefore, this translates into the first derivative of f equals 0. Now let me just draw a graph. I want you to see. So remark. The graph of f is given by the following. So let me just draw it. So these are the axes, x-axis, this is the y-axis. And now I'm gonna, so here, let's say I have this point, negative 5 over 3, whatever. So this will pass through this. It will go here, will go through here, and it will go like this. Okay. So here we have, let's just say here we have 5 over 3. Here we have 2. And here we have, so let's say here we approximately we have 22 over 27. Here we have 1/4. We're going to have the tangent line, right? Of slope 0, right? And the same here will happen here. Of slope 0. So the tangent line will be horizontal here, right? And let's just say here we have, this will be -3. Yeah. And here we'll have 2. Here we have 1.3, so something like this. Anyway, so this is how the graph will look like. All right, guys, I think I'm going to stop here. Well, I don't want to do too much, but there will be another video coming, and in this other video, so I decided to split this lecture into 2 lectures so that I don't want to have one very long lecture, like 3 hours, whatever. It's also very late as well. The next lecture that will be available very soon, maybe today, tomorrow, we will be talking about the derivatives. You will see more derivatives rules for trigonometric functions, for sine, cosine, secant, cosecant, whatever, and also for the exponential and logarithmic functions. And also after that, we will be talking about the examples of how to apply the chain rule. All right, thank you very much.